What is up, guys? Welcome to another video brought to you by The Simple Engineer. In today's video, we're going to talk all about database indexes or database indices and performance. We'll talk about why you want to use an index. We'll cover what an index actually is, talk about how to create indexes. We'll be using PostgreSQL as our RDBMS engine. We'll look at explain and analyze the commands and why those are useful. Some philosophies around creating indices, different algorithms for indexes, and finally, clustered versus non-clustered indices. So a lot of information to cover, so let's just dive right into it. So first thing I want to do is talk about a relatable example for indices. Let's imagine that we have a deck of cards, okay? And the question that we need to find is, we want to find a 2 of hearts. And so what we do is we start at the top of the deck and we kind of linearly work our way to the bottom of the deck to find the card that we're interested in. And you can see that this is not really an optimal way of doing this. You may think, well, what I can do is I can actually segregate my cards based on the suit, okay, hearts, spades, clubs, etc., and then I can kind of do a lookup from that way. So it would look like this. If I ask that same question, then I go to the hearts column and I can almost instantaneously find the information that I'm looking for. And likewise, if I look for something like the 4 of spades, I can look at the spades column and almost instantaneously find the value that I'm looking for there. And this becomes a linear search just on that specific pile, right? And so this is kind of the idea. Now, let us kind of answer the question, what is an index from a technical viewpoint? So when we're talking about database indexes, we get this huge benefit where we get quick lookup on rows that match a specific criteria. And it's nothing more than pointers to physical data within the table. And we'll look at this structure in a lot more detail. But the idea is that when we search our data that's sorted, right? So indices are going to be sorted. We know that searching on sorted data is really fast. So without an index, we get that linear search time that we saw with the deck of cards. But when we're searching through sorted data, we get logarithmic search that looks something like this. And that can be a highly, highly performant thing to have when you're doing searches on large volumes of data. Now, the caveat with all of this is it's going to require a lot more writes and a lot more storage. And so it's going to be kind of a business trade-off decision to figure out how many indexes you want and where you want them. When we're talking about single indexes on a table, it's going to look something like this. So we have a very simple person table with an internal row ID that's unique and auto-incrementing. We have a name and a state. So what we're going to do is create a non-clustered index, and we'll define that later, but we have a structure where we essentially have all of the states that are alphabetically organized, and then it's going to have an internal row ID, which is kind of the lookup pointer. Our search criteria is filtered on state being Arizona. And so what we do is we kind of find, we do a binary search to find the state, and then we realize there are actually 2 values that match this criteria. And then from here, we do the dereferencing lookup to the physical table to get the columns that we're interested in. We can get a little bit more performant based on the queries by doing something known as a composite index. And this is going to have a precedence defined. First, we have an index on state, and then all of the names are sorted based on the state. So you'll notice that state is alphabetical. And then if you look at each state like Massachusetts, New Hampshire, Arizona, the names are alphabetized just in that subgroup. And this can get us super, super high performance if we're doing queries that utilize both of these sort of queries in the queries that we're executing. And so here I have kind of 2 criteria, state and name. So I basically do a binary search to find the state that I'm looking for. And then within that subgroup, I do a binary search on the name index. And then from here, I can do the dereference lookup operation to the physical table. Now, in this case, I actually have all the information that I was looking for in the composite index. So I could almost even be more efficient, and I wouldn't even need to do an additional lookup if I was just interested in state and name, because it would all be located in the composite index itself. And that's something known as an index scan, and we'll define that later in this video. Now, when you're doing something like a composite index, when you have multiple indices that depend on one another, there's a precedence. And therefore, order is going to be extremely important here. And so this, you cannot say if you have an index on column A and column B together, it's not equivalent to saying that you have an index on column B and column A. And that's because you are physically reordering the table structure, right? And the precedence is going to be defined from left to right. And we'll give a couple examples of this. So let's say that we basically have an index, a composite index on date, age, and name. If we make a query where we specify the date and we specify the age, then kind of similar to the previous example, we can almost instantly find the information we're looking for. And that's because we can first do a binary search on date, then do a binary search on age, and then we can get all the information that we're interested in. Now, if we do a similar query where we're looking for date, we skip age and then name, then we've just kind of violated this order precedence, right? Because now that we are searching for name without the age present, name is not sorted on date. Therefore, what we end up doing is first we get to exploit, yes, we do have an index on date, so we can find this section very quickly. But because we didn't specify age, we effectively need to do a sequential scan within this subsection of date. And so we start at the top and we have to linearly scan until we find the information that we're looking for. And so you have to be very careful when you're doing these sorts of queries and composite index creation. If you take an extreme example, basically we have age and we have name. And many people think that because I have the 2/3 of my index, this lookup will be still pretty fast. But that's not the case because age and name are not sorted in any special way if a date is not present, right? So it's effectively you're searching the heap in a sequential way. And so you basically, for this query, have to start at the top and do an entire table scan to find the information that you're looking for, because nothing is sorted in this case. You would need to specify date to exploit this composite index. Now, if you had a separate index on age, for example, or a separate index on name, then you could optimize this. But there are, of course, trade-offs because that can get a little bit more expensive as well. So that kind of brings us to the next topic, which is indexing philosophies. So just a couple points to harp on here. The first thing you want to be curious or think about is you want to create indexes on highly selected columns. So if you're going to have queries that are not going to be referenced a lot by your downstream users or your downstream applications, you're not going to want to create an index on that because it's not going to benefit you in any way. You don't need to necessarily create an index on queries that aren't going to execute a lot because it's going to take time and space. So the second point is that you want to think about the implications of updates and deletes. As you build indexes, these indexes need to stay in sync with the actual table. So if you delete a row from the table, you also need to update all of the values in each respective index. And if you have a lot, that can be very expensive. If you're doing a lot of updates and deletes, then you have to really think about how much data do I have? How many things am I going to update and delete from each index after each one of these operations? And the sub note here is that you really need to understand your queries. What are the business people doing? What are the developers downstream doing against this table? From there, you can create your indexes based on that. When you're building tables in databases, you build them based on the relationships between the data. When you're building indexes, you build them based on the query use case, how often different columns are selected, how often different queries are executed. And that's why you really need to understand your queries to be able to build your indices. So that's very important. The final note is that you don't want to over-optimize too early, right? As I had said, indexes are expensive. You don't want to throw an index on every column, right? That's going to kill your performance. And so you want to kind of fine-tune over time. And that brings me to a note from one of my favorite computer scientists. Premature optimization is the root of all evil, Donald Knuth. Very true point, so always kind of have this idea in mind. So moving quickly along, let's kind of talk about creating indexes from a physical RDBMS perspective. Like I had said before, we'll be using Postgres as the example. So basically, to create an index in Postgres, the syntax is kind of like the following. So you specify create index, you simply put a name, and then you say the table that you want to create the index on, okay? If you want to build a single column index using a different column, so this would be a non-clustered index here, then you basically say, you specify the index name, the table, and the column that you're interested in. You can do a multi-column or composite index by very similar syntax, but you just comma delimit the column names that you're interested in. If you want to enforce data integrity a little bit further, you can do a unique index where you basically prefix this unique flag in front of the index and do the same exact thing. And this will ensure that every single value in that column has to be unique, or you'll get an error upon insertion or update. The final thing is a partial index. We didn't talk too much about this, but it's a way to save on space and performance a little bit. And basically, it's the same thing, except instead of a column name, you can put a conditional expression. So you could say on table name where car type equals motorcycle, for example. So you can kind of have these filtered expressions in your partial indices, and this can really improve your performance. Now, speaking of performance, this brings us to this idea of explain and analyze. So in order for us to understand how to performance tune, we need to understand these two ideas. So explain and analyze basically facilitate index tuning, and they show you how your query is going to perform. So explain is going to display the query execution plan, exactly what the RDBMS engine is going to do. And explain analyze is going to actually run that query against your database and provide you some more realistic statistics around that query. You want to be careful with explain analyze, because if you are running a drop statement, for example, it will physically drop all of your data, and you want to be cognizant of that sort of operation when you're doing these sort of performance tunes. We'll look at an example, but before we do, just so you're not confused, there are a bunch of different scan types that are going to be present in the query execution plan. And we'll start with the sequential scan. So a sequential scan in the plan is going to say that we are effectively scanning the entire table, right? So if you have a billion rows, the computer is going to literally look at all billion rows. So it's very slow, and it's a brute force approach to how this information is going to be retrieved. When we look at something like an index scan, it's going to be a lot faster because it's only scanning rows within the index, and that information is going to be sorted. Okay, so that's logarithmic lookup. And then from there, we do lookups in the heap. So that's kind of that dereference operation. If we have all the information in the index itself, then it's considered an index-only scan, highly performant, right? That's going to scan either all or some rows in the index, but no further lookup is going to be required. And then finally, the kind of most complicated thing to understand is a bitmap heap scan or a bitmap index scan. And we'll look at this in more detail. But effectively what happens is we scan the index, we build a bitmap of pages to visit, and then we look up only the relevant pages. And we'll look at an example of this. There was a user on Stack Overflow that had a pretty good example of looking at these explain commands just so we can understand the syntax of what it looks like. So we have a test table. It's a 3-column table, and we're just inserting some dummy integer values. Okay, so we have a primary key, which is going to be a clustered index on A, which is an integer. We have a unique constraint on B, which is an integer, and then finally just a random C column, also an integer. When we do a explain and we select everything from the table where every value is not 4 for the A column, then what you see is we see a sec scan. And a sec scan is a sequential scan, effectively starting from the top of the table to the end. And although this is a very contrived example, if you had a billion rows in your table, it would look this exact same way. And it would basically tell you that this is going to be a highly expensive query, okay? And that's what a sequential scan is going to look like. When we're looking at an index scan, this is going to be highly performant because we are targeting a clustered index where A equals 4, and we do a logarithmic search to find that value. And so from here, we only need to look in the index and we get the information that we are basically filtering against. So this is going to be kind of an ideal situation here. The final one that I want to kind of talk about quickly, and then we'll look at an example, is the bitmap index scan. And so here you see that we have 2 filter clauses here, A equals 4 or A equals 3. So we do an index scan, and basically anytime that we see something in the index that satisfies that criteria, we build a single dimensional array and we mark the value as 1 if it's true. But we don't do any lookups. We don't do any dereferencing to the physical table. So we take both of these bitmaps and we OR them together. And then the bitmap heap scan is going to basically look at all rows that have a 1 as true in the bitmap and then do dereferencing in the heap against that. And so that's kind of the performance that we get there. We do a lookup with the final bitmap. And the way that you read these explain queries is you start from the inside and you work your way out. Okay, so the innermost part of this explain plan shows you the operations that are going to happen. And then as you work your way out, that's kind of the parent operation that gets performed on the inner, kind of like a mathematical function. Okay, so let us kind of understand this bitmap idea a little bit more through an example. And this is a little bit confusing, but we'll talk through it. So let us assume we have a simple query. We're specifying an AND clause with both date and age present. And for this example, we're going to assume that we have a single column index on date, and separately we have a non-clustered single column index on age. And so when we're talking about a bitmap index scan, we're effectively performing an index scan like we would otherwise, but instead of dereferencing, we create a single dimensional array where we encode a 1 if that primary index filter is satisfied. So for example, if the date was August 15, 2020, we would just encode a single bit of a 1, and that encodes the heap file locations. But the point here is that we don't access the rows in the heap file yet. We're going to do that at the end. And the thing that does that is the bitmap heap scan. So the heap scan is going to scan over that heap file once, but it's only going to look at rows or pages that have been marked a 1 in the bitmap. So if you have a lot of working memory, then you have the granularity of rows. But if you don't have a lot of working memory, then you actually do it by kind of a page. Because this bitmap exists as an in-memory data structure, if you only have, for example, 64 kilobytes of working memory, then you're probably going to have coarse-grained a lookup, which is going to be based on pages, not the physical rows. So kind of what this looks like from a visual perspective is imagine that we have a B tree. We'll look at this data structure at the end. But we perform a bitmap. We recursively descend to the leaf nodes. And for every row or page that matches this initial filter criteria on date, we'll get a 1 encoded in the value. And then we'll do the same thing for the age index. And then we'll mark everything as a 1 that satisfies that age equals 6 criteria. And then since we're doing an AND, we do a bitmap logical AND over each of these single dimensional arrays. And then the heap scan is going to execute over that final output. And that's kind of where the dereferencing begins to retrieve the data. And that's kind of what's happening when we're seeing bitmap operations in the explain execution plan. So you've heard me talk about clustered versus non-clustered indexes. Let's kind of look at what that means in more detail. So a clustered and non-clustered index kind of looks like this. For a clustered index, we start with a root. We have a bunch of nodes in the intermediate layer, and then our data nodes are at the leaf, okay? Each intermediate and data layer are connected like a doubly linked list. So this allows us to traverse to nodes within the same level without needing to recurse back to the parent. And then the parent-child relationships are connected like so. And so what we do when we search, we kind of do a binary search for optimal search efficiency. And we go through the tree until we get to a data node. And the data nodes, or the leaf nodes, are where the actual table data exists. This is where the information is. Now, the caveat is you can only have one of these per table, and that's because you physically reorder this is the table. So you're physically reordering the order of the table based on whatever your clustered index is. So a lot of the times you have a primary key, it's an auto-incrementing integer. You physically reorder the table's sorting structure based on that primary key. Okay, that's an example of a clustered index, a primary key. Now, a non-clustered index, you'll notice that the structure is almost identical. The differentiating factor here are the leaf nodes, and you'll notice they're data pointers. And effectively, they point to the data in the actual table. And so you can think of a non-clustered index, it copies the data that represents the pieces of the index, but it doesn't copy everything. And that's why they still take a lot of storage, but not as much storage as copying the entire table. And so you start at the root, You work your way through the nodes, still binary search, but when you get to a leaf node, you do a data lookup to the physical data node in the actual table. And that's kind of the operations that occur. So when you compare and contrast these two, clustered indices, the rows are physically stored on disk in the same order as the index. Okay, this is not completely and holistically true here, but the point is that in chunks, the data is the physical bits of this information are encoded on the disk in the same order as the index. Only one of them can exist at a time. Okay, so like I had said, it physically reorders the structure of the table. And it's typically easier to read if you want to look up all the columns. Okay, so if you're looking at a clustered index, all the columns are going to be in that physical table. So if you're looking at just the clustered index value, you can get your information faster because you're not doing as many lookups. For a non-clustered index, it's kind of a secondary list or an auxiliary data structure that has pointers to the physical rows like we had just seen. And in theory, you can have infinite number of non-clustered indices. The caveat in this case here is that you can have extreme performance degradation if you're doing a lot of updates or deletes. The non-clustered indices always need to stay in sync with the table. So if you delete something from the table, you need to go and update all of your non-clustered indices to support that change or update. The final point that's going to get a little bit more detailed here from a theoretical perspective are database search algorithms. When we're talking about something like a linked list, and we are asked to find basically somebody's last name, you can imagine a linear data structure like so. It's connected in this sequential way. And the best that we can do, like a sequential scan, is start at the head and kind of linearly work our way through this data structure until we find the information we're looking for. And this would be complexity in the order of n, which is linear. You look at every n elements. We can further improve this when our data is sorted, right? And this is a binary search tree. We start with a root node. We have at most 2 children, okay? And imagine we have a bunch of last names. Now, the question is the same. We want to find this person. So we start at the root node and we say O is going to be before S. O is going to be before R. And we know O is going to be after A. So at each subsequent level, we actually half our search space because there are at most 2 children. And so if we half our search space at each level and we look at a graph, we can say that a linear graph is going to look like this. But if we half our search space at each level, we actually get a logarithmic graph. And that can be extremely, extremely performant for this sort of sorted data. Okay, so this would be order of log n. Now, the caveat with this sort of data structure is that as you add more and more nodes, if they satisfy this criteria where a node is before another node, you can actually get an unbalanced tree. And this effectively turns into what you would see in a linked list, right? This is complexity, linear complexity, and that can really kill your performance. And so databases go another level and they say, I have this thing called a B tree. And a B tree is a self-balancing tree. And this is a whole topic in itself, but the point is that the leaf nodes are always at the same level. So it reorganizes the tree to support inserts and updates and deletes in this way. So if we were to insert 100, we'd have a root node, okay? If we were to insert 90, it would stay at the same level. So we have multiple keys in a singular node. Now, if I insert 80, for example, you'll notice that we reorganize the tree. So it self-balances and we satisfy that criteria of all of the leaf nodes existing at the same level, okay? If we insert 75, we have, so the max degree in this case is 3, so we have 75 and 80 in the same node. Now, if we insert a 50, we really reorganize the table such that all leaf nodes are at the same level. And this sort of reorganizational structure still exploits binary search, but we get guaranteed logarithmic complexity. And that guaranteed logarithmic complexity is what databases exploit to search through their sorted data. And so this kind of summarizes some of the search algorithms that you can think about when you're dealing with large volumes of data. So that kind of concludes this lesson. Thank you guys so much for watching. Please feel free to leave a comment if you have questions and subscribe. Thanks.